This equation is both separable and linear. I'd like you to solve it both ways. Make sure we understand it. So which way are we going to do it first, separable or linear? Okay, if I'm going to do it separable, I need all the x's on one side and the y's on the other. Then I integrate. Left side is of what?
Y.
Right side?
Negative ln of x.
There's got to be a plus c somewhere. We'll put it on that side. I want an explicit y equals. What do I do? Say again? E's and ln's cancel, but the minus sign's in the way, so I do. And that's going to make it an x to the minus 1. I'll also separate that e to the c. And that'll account for my plus or minus here in the absolute value here. So then I get y equals the e and the ln cancel. I get x to the minus 1 times some number over x. Please notice, works when x is less than 0, works when x is bigger than 0, doesn't work at 0. 0 is a singular point because we divided. So the absolute value part went away because I can have different answers when x is negative versus x being positive, depending on my initial condition. If I kept it here, then this would be y equals absolute value of 1 over x. But I could then say, oh, well, that's 1 over x with a positive number or a negative number when x is negative, or a positive number and negative number when x is positive. So really, I can absorb the absolute value into this constant by changing the sign to be plus or minus as needed. Okay, that's separating. It's also linear. How do I do it that way? I need a little more than dy by itself. I need dy dx. Then I should just divide by dx. If I divide by dx, I'll end up with a dy dx here, right? I'll end up with something that's just y here. That's okay. Okay, wait a minute. That's something times y prime and something times y, right? The other side is 0. No matter what I do when I integrate, that other side, that right side is going to stay 0. The integral is 0, 0. If I multiply in my integrating factor, it's going to be multiplied by 0. I don't have to worry about the right side. So let me look at that left-hand side for a minute. What's my integrating factor?
It should be. dy dx.
Ah, wait a second. That's the form I need. Remember, it's y prime plus p of x times y. P of x isn't times the y prime, it's times y. Okay, so I had to rearrange a little further to get myself to the standard form. Now I have the p of x. So what's my integrating factor? Almost. That's p of x. P of x is 1 over x. How do I get the integrating factor from that? E to the integral of 1 over x. Wait a second. It's the integral of 1 over x. And then I have e to the natural log x. What happens? Which means I get right back to here. When I multiply everything by this, I get x dy dx plus y equals 0. Which means this is already set up as the product rule derivative of something. We basically went in a circle because we didn't notice that it was already the product rule of something. What's the product rule? So this is the derivative of what? Exactly. The integrating factor times y. Now I have to integrate. So I get xy equals the integral is 0. A constant. C. Which means I get y equals C over X. I got the same thing. It's nice if we can notice that this is already set up as a product rule derivative. The derivative of x is 1, the derivative of y is dy dx. We could have just gone directly to there if we recognized it as the derivative of a product rule. As a matter of fact, I think it was you asked me this yesterday, didn't you? How do I always have to do that? Well, only if it's not rigged. This one was rigged. But if you're not noticing that, we still do it the long way, we get exactly the right answer. Very happy with that. But if I go back to the beginning, y dx plus x dy. That was how this left-hand side started, yes? Chapter 3, section 10, all the way back in Calc 1. And then a little bit later, in Calc 3, we did the chain rule in chapter 14. Let's consider the function xy as a function of two variables. In chapter 3, in Calc 1, we talked about differentials. And in chapter 14, we said, oh, the chain rule allows us to do differentials. So I could say, hey, what is dxy? What is the differential here? Well, the differential is the partial derivative times the differential of the variable. So this would be the partial of f with respect to x times dx, and the partial of f with respect to y dy. This is called a total differential. But with our function, what's df dx? What's this derivative for this function? Just y. And df dy? It's already the derivative of xy, which is what we found when we were doing the setup to be linear. If I have some function then the differential looks like that. If I know that my differential equation already looks like that, equal to 0, then I'd take the integral and I would get f of xy equals a constant. Okay, wait a second. Wait a second. Chapter 16. Stokes theorem, Green's theorem, all that crap. We talked about potential functions. Functions that had nice curl and divergence and all of that crap. And I would say, hey, you know, if the gradient gives me this nice anti-derivative, so I'm trying to find a function where I know it's partial derivative of x and I know it's partial derivative of y, that's the gradient of f. And if I want to find the gradient, I had to do two integrals and then make them match up, right? I had to reconcile the integrals with one another. I had to take the derivative of the other variable. There were several different ways of doing this in the textbook. We called this function f a potential function for the vector field. Hang on a second. Here's a differential equation. Make it equal 0. Then it's an equation. Otherwise, it's an expression. Sorry. Here's my differential equation. If I assume, we'll figure out whether or not I'm allowed to assume in a minute, but if I assume that these are the derivatives with respect to x and with respect to y of some function, how do I find that function? So take the integral with respect to the right variable, yes? So to get f from here, I would say, oh, I got x squared minus x plus some constant. But wait, that constant, that's only a constant in terms of the x variable. That thing could have y's in it. So I'm going to write it as C1 of y, because it could have y's. It might not, it might just have a constant, but it could have a y in it. What about over here? If I use this, then what's f?
Five, two, seven, five.
That's a y to a first power. So,
3/2 plus 9.
and then the 7y. But again, there could be a constant here, right? But this constant is only constant in terms of y, which means it might have x's in it. I want to call it C2 of x. Now, my question is, can I make these match? Is everything that appears in that function on the left somewhere in this function on the right? Is everything that appears in this function on the right somewhere in that function on the left? Yes. If I think of the x squared minus x piece over here, that's hiding in this. And if I think of the 3 halves y squared plus 7y over here, that's in this. So really, this function should look like this. And the answer is, so what? this function is the antiderivative of this. Our differential equation is now solved. This is the function that satisfies this, because if you take the differential of this, that's what you get. I just moved the c to the other side and didn't bother to make it negative because it's a constant. Constants can be positive or negative. Problem. This is not an explicit solution. This is an implicit solution. This is not y equals a bunch of stuff. I could rewrite it if you really wanted to solve to make it y equals. But that requires me using the quadratic formula, where this is the constant term. Y squared, y, and number. I don't like it. We can do it, but it sucks. I'm perfectly happy to leave my implicit solution. I don't mind at all. We can leave it like that.
Why is it equals?
Well, because I set it equal to 0, like I did up here, but I just moved the c from the left side to the right side. And so minus c is just another constant. Graphically, when we talk about the potential function back in Calc 3, a function of two variables, this is a level curve. For a particular value of c, this is a level curve of this surface, f of xy. So if you wanted to, you could graph this in 3D, pick some c values, and you'd be able to get a graph of the solution. I can see you all are thrilled by this idea. But we did talk, actually, I think it was week 1. We talked about the idea of writing a differential equation as some big function of x and y prime all mixed together. We talked about writing it y prime all alone. We also talked about writing it in this differential form. So let's consider a differential form. An expression m of xy dx plus n of xy dy is an exact differential in some region R of the plane if it corresponds to the differential of some that function. In other words, if partial of f with respect to x is equal to m and partial of f with respect to y is equal to n. So I'm looking at this thing on the left of the dx and the thing on the left of the dy, and I'm asking, is this the derivative of something already? Like in my product rule setup. Maybe it's not a product rule, maybe it's something bigger and uglier, but maybe it's just the derivative of something. Then I can integrate and walk away. If I have an ordinary differential equation where that left side looks like this, we're going to call that an exact differential equation. And now I'm going to ask you a very loaded question. We figured out a way to tell whether or not we could have a potential function for a function of two variables. In Calc 3, we did this. It was part of Green's theorem. It was part of Stokes' theorem. It was in the very last chapter we did in Calc 3. How the hell do I know whether or not this expression is exact? And it has to do with what we were doing in partial derivatives. Right here at the top of the screen, I said if df dx is equal to n and df dy is equal to n. So I want to know, is there a function that does that? How can I look at m and n and figure that out? Hmm. Somebody Google Green's theorem. What does my buddy Green have to say in his theorem? And if reading Green's theorem still makes you go, huh? Then look up conservative vector field.
Is it a vector field that can be expressed as the gradient or scalar that's a function?
Right, but that's the function we're trying to find is f. So now the question is, how do I find that f? What tells me whether or not a vector field is conservative or not? In Green's theorem, we were using P and Q and R for the three pieces of our vector field when they were 3D, just P and Q when we were in 2D. So I'd really only be dealing with P and Q.
It says F equals delta. It's a Greek letter.
Cross, right? It's an upside down delta.
Yeah, it's upside down delta.
Cross that scalar function f, the vector field. That's the curl. And in 2 dimensions, the curl comes from Clairaut's theorem. I need to look. Let's suppose we had this. If m is the partial derivative of f with respect to x, then what is the partial of m with respect to y? Well, by definition, that's the second derivative of f with respect to x first and y second. We would write that as fxy if we were using the subscript notation. In partial derivatives, when we did second derivatives, we said this is a mixed second derivative because it's got x's and y's mixed together in the derivative down here. There was something nice about mixed derivatives. Nx equals. That's again the second derivative of f, but this time it's respect to y first, then x, so that's fyx. My buddy Clairaut told me that whenever I do second derivatives, the mixed second derivatives are equal to each other when f is continuous. So it turns out this is exactly the criteria I need. If I want to know whether or not my differential equation is exact, I need to know if those two things are equal. That's all I need to know. And then all I have to do is the same integrals we were just doing. First question is this exact? If the answer is yes, then I want to solve it. What's m? What's n? Right, because it's m dx, n dy. So I need to know what the partial of m with respect to y is. My, that's the derivative with respect to y of 5x plus 4y. I get. Hey, that's easy. Nx, that's the partial with respect to x of the other piece, 4x minus 8y cubed. What do I get? The same blessed thing. Which means the function I want can be found by integrating m with respect to x, n with respect to y, and reconciling those two. F is the integral of m dx and the integral of n dy. So now that we know it is exact, we can solve it, get whatever function we have and set it equal to c, Cody. Just set it equal and put the c on the other side. So I need the integral of 5x plus 4y dx. What do I get? Plus some constant that might have y's in it. To do the integral of n, it's the integral of 4x minus 8y cubed dy. I get
Minus 2y's plus C2 x.
right. So now my question is, can I reconcile these? What's the combined thing? If I try and glue these together, does everything in the top row have a place to go in the bottom row? Does everything in the bottom row have a place to go in the top row? What's my resulting answer? No, I count this once because it's in both.
Or no, you said you count that one.
Right, that's the same thing, so I only need it once. Equals some constant. I would make it plus c equals 0, then I'd move the c to the other side, I might have put it on the other side to begin with. Presto.
Okay, my question was, when you do that, why is it negative?
Well, because a constant's a constant, whether it's positive or negative, right? So I just absorb the minus into the c.
If the 4xy and 4yx were different,
Then I'd have a problem. And if I can't reconcile it, it means I did something wrong up here. If this works, this has to work. So if I make a mistake up here when I do my partial derivatives, then doing my integrals is going to have things up all the time.
so it should always be the same.
The pieces that are mixed should always be the same. I think this is problem 13 out of the text, so that you know I'm not just making up out of thin air. But this doesn't even look like it's in the right format to begin with. It's not set up like it could be exact. So I need to do some algebra to rearrange first. So I'm going to start by moving the dx over here. And then, what should I move to what side? for us to determine whether or not this is exact, my normal look is m dx and n dy. So I already have m dx on the right-hand side. I should probably move the other piece over. So I'm going to move the dy part over here. Now, important thing. I said it was m dx plus n dy. If I move this over, it should be negative, right? I'm going to write it like that to emphasize that I know I moved it over and made it negative. Is this exact? Because my is -1 and nx is also -1. Perfect. It's exact. So my potential function is found by doing this. And now I just got kicked in the pants. Because I have to integrate with respect to x. All that stuff in that first set of parentheses. That's the integral of 2x e to the x minus y plus 6x squared. And that's got an x e to the x in it, which means I need to do integration by parts. I did it on my scratch paper. When you integrate x e to the x, you get x e to the x minus the integral of e to the x. So I get another minus e to the x. And the 2's just carry through. But the other part's really easy. What's the integral of minus x dy? Piece of cake. Now I realized as I was writing down that second integral, I forgot something up here on this line, and I forgot it down here as well. What's missing? My plus c's. So up here, there should be a plus c1 of y, and down here, there should be a plus c2 of x. Does everything have a place to go or a match in the top and the bottom? I see the minus xy in both places, so I need that. And then this can eat up all the x stuff, and there's nothing in here. There's no all y stuff for me to put there. So that piece is empty. Perfect. So f of xy is minus xy plus 2x e to the x minus 2 e to the x plus 2x cubed equals some constant. I have absolutely no idea what that thing looks like. By the way, though, you could actually write that equation y equals, couldn't you? Move all this crap over to the other side, divide by the negative x. You could graph this and know exactly what it looked like. If I have an initial condition, I can solve for C. In this problem, that would suck because I'm going to have that E floating around in there. And unless my initial condition is at a really nice X, that's not going to make my life easy at all. Questions? I'm just going to write this problem down. I'm not going to do it right at the moment. 4y plus 2x minus 5 dx plus 6y plus 4x minus 1 dy equals 0. But this one has an initial condition. Y of minus 1 equals 2. This is exact. Partial with respect to y over there is 4. Partial with respect to x over here is 4. That matches. We can do this. When all is said and done, and you do this problem, you actually end up with a curve that you should recognize. May take a little bit, but this equation has as its solution a hyperbola. By the way, when we solve it, we end up with this constant d8. So I put it on this side this time, put it on the left rather than the right, because if you graph this, this is a hyperbola. I believe that grapher file that shows this graph and the differential equation in slopes, or in grapher, I don't remember which, is on our Canvas page. Questions? Yeah, shaking your head at me. What's going on? They don't equal each other. This equation is not exact. Well, I'm up the creek, right? Can't do anything. Wait a second. With my linear equations, Sometimes I didn't have something that was already a product rule, but I could multiply something in and make it a product rule, right? So maybe it's possible for me to do the same thing here. Maybe there's an integrating factor trick. Well, then I would have a new equation. And I would want this equation to be exact. Which means I need to check the partial derivative of this thing against the partial derivative of the other. Oh, crud. Wait a minute. I need the partial derivative with respect to y here. But this is a product. So I would have the partial derivative of y times m plus mu times my. And I would want that to be equal to the partial derivative with respect to x times n plus no partial nx. Ew. That's nasty. I'm trying to find a function whose derivative in x and derivative in y match this sum over here on the right. No. This is a partial differential equation. I have no clue how to solve this. Unless I get lucky. If one of these partial derivatives of mu is 0, then I can do this. If mu y was 0, well, then I would have mu my equals mu xn plus mu nx. I want to put the mu parts together. So mu xn is mu my minus mu nx. Okay, wait a second. Wait a second. That's separable. I can write d mu over mu, and I put a dx over here. Which means I have an integrating factor. I have an integrating factor that will only be in x because I'm only integrating with respect to x. So if this expression up here is only x's, then I can find an integrating factor. By the way, there's another version if it's only y's. So there are two different integrating factors, depending on whether or not I can cancel out things in my partial derivatives to get one variable and one variable only. This looks fucking insane. I promise it's less insane than you think it is. It's not completely uninsane, but it's less insane. Here is an example. Consider this equation. Is this exact? No, because my is 4y and x is 2y. Oh, wait a second. Those are only in y, aren't they? Let's look at our two special equations. I have this one that has an m on the bottom. If I did this minus that and divided by this, would I get rid of one variable? Nx minus my over m would be 2y minus 4y over that. That's not one variable, right? That's still got two variables in it. So let's try the other one. Let's do my minus nx over n. What's that? Aha! Oh, what's my Daffy Duck? Aha! Really practical. That's what I'm going to use. I'm going to use my integrating factor here. E to the integral 1 over x dx. What do I get? This is mu. Because I get e to the ln and then the e and the ln cancel out. Beautiful. Let's use this up here. My new equation, 2xy squared plus 3x squared dx plus 2x squared y dy. I multiplied everywhere by an x. And now I'll ask the question, is that exact? Because here, my is 4xy and nx is 4xy. Hallelujah, I got an exact answer. Well, I have an exact differential, which means I can integrate to do the answer. F is the integral of m dx, and it's the integral of n dy, and I have to reconcile those two pieces. Und so we integrate. What do we get? And the x cubed is hiding in here, and this is empty. So my function f of xy that satisfies our differential equation or x squared y squared plus x cubed plus c equals 0, depending on whether you want to write it explicit or implicit. I don't really care. But I was able to find a way to turn a non-exact equation into an exact equation. If we had more techniques for figuring out how to deal with mu in two different derivatives, in partial derivatives, if I didn't have to hope that one of these would cancel out completely, there might even be a way to do this as a function of x times y, treating that like it's one variable t. Or maybe it's a function of something radial, like x squared plus y squared, shifting to polar coordinates or something like that. There are lots of other options. But the important piece here was that I could find a way to cancel one variable out in my integrating factor, and the result was something that worked. What about the other one we had? X squared minus y squared dx plus 2x squared y plus 4 dy. We had my equals minus 2y and nx, 4xy. Let's take a look at our two possible reactions. I have my minus nx over n, and I have the other way around, nx minus my over m. Those are the two possible, quote, simplified versions. Compute for me. Do either of these resolve to one variable? That should be a 2, not a 4. I was hoping something would cancel. But even when I try and factor and see if something cancels out, it doesn't. Which means the method of integrating factors is not sufficient to solve this problem. There's got to be another way. I don't know what it is right now, but it certainly isn't any that we've done so far. Well, damn. So here's a case where neither of my potential integrating factor resolutions worked for me. Questions? Tomorrow's question and answer day. You should bring me lots of questions. All right? That's chapter 2, sections 2, 3, and 4. Right? Separable, linear, and exact. 3 whole categories, all nice, direct behavior. It may mean that we're doing some messy looking integrals between here and there. That's why it's Calc 4. We got to do some integrals here. I will see you all tomorrow. Have a wonderful rest of your day.